Hello everyone. Am I audible to all of you? Am I audible to all of you? Am I audible to all of you? I'm waiting for your reply. 3 students has replied that I am audible. Is my screen is visible to all of you? Is my screen is visible to all of you? Students are replying that yes, the screen is also visible to all of them. Okay, so let us start today's session. Hello everyone, good afternoon to all the students. We are starting the video lecture series on microprocessors and microcontrollers theory. We are discussing chapter number 5 of module 3, which is the last chapter of Intel 8086, and this chapter is all about Intel 8086 interrupts. This is our lecture number 1. First of all, what is an interrupt? We all know it is one of the most important features in the microcontroller or microprocessor applications. And in this chapter we will explore the concept of interrupts and interrupt programming. Consider a microprocessor system receiving data and change in status from I/O port or device. There are 2 methods available to obtain the input. One is by using the polling method and another is by using the interrupt method. So there are 2 options through which the microprocessor can able to communicate with the input device. One is polling, another one is interrupt initiated I/O. In interrupt method, whenever any device needs to service from microprocessor, the device notifies the processor by sending the signal called interrupt. For example, suppose there is an input device and that input device needs to communicate with the microprocessor. Then this input device will send INTS signal or trap signal, INTS signal or RST signal, whatever, to the microprocessor. Upon receiving the interrupt signal, the microprocessor holds whatever it's doing and serves the corresponding device. That means, suppose the microprocessor at that point of time is executing a program P, then it will stop that program P and will inform that input device with the help of INTA bar that it is accepting its request. So the program associated with the interrupt is called interrupt service routine or interrupt handler. So whenever microprocessor MPU is handling this interrupt, so it is using the special sub interrupt routine or special program known as ISR. Each ISR has a unique address known as the vector address. Next is polling. In polling method, microprocessor continuously monitors the status of the given device. When the status condition is met, it performs the service. After that, it moves on to the next device until each one is serviced. Although polling can monitor the status of the several devices and serve each of them if certain conditions are met. So let us explain polling. Suppose I have an input device and I have a microprocessor unit MPU. Now the input device has microprocessor is continuously taking a watch on the input device whether it is sending any request to the microprocessor or not, and at that point of time microprocessor is not doing anything. Whenever the input device has sent the request, microprocessor will send an acknowledgement request or ACK request. Okay, and input device will able to know that microprocessor is ready for communication. Then microprocessor will give the input device the necessary service. After the service is over, the control once again come back to the microprocessor, and microprocessor starts execution its normal program, that is say P. An interrupt is a condition that causes the microprocessor to temporarily walk on the different tasks and then return to its previous task. Interrupt is an event or signal that requests to attention of the CPU. Example. For example, suppose X is an input device. X is an input device. So there is an interrupt occur or exceptional condition occur, so it will obviously request the MPU for giving the service. In order to request it, it will take the help of the INTS signal or NMI signal. Okay, and upon receiving this request, microprocessor will send INTA bar signal. If the INTA bar signal is 0, then accepted, and if it is 1, then interrupt is not accepted. Whenever an interrupt occurs, the processor completes the execution of the current program, and starts the execution of the interrupt service routine or interrupt handler. And ISR is a program that tells the microprocessor what to do when interrupt occurs. After the execution of the ISR, controls return back once again to the main routine. So let us explain that. So microprocessor is suppose executing a program, say P, and the P contains the 50 instructions. So currently suppose it is executing 25th instruction. So microprocessor will complete the 25th instruction. Naturally, the next instruction, 26th instructions starting address, it will store it in a stack. Okay, then what happens? Microprocessor will call the ISR of which will handle the interrupt occurred in input device X. That ISR has a starting address. So let me assume this is the ISR or starting ISR. Let the starting address of the ISR is XXXXXX. Okay, and we have the rate instruction at the end of the ISR. So its control will comes to the ISR. It will execute each of the instructions of the ISR, and whenever the rate instruction is performed, control will return back once again to the microprocessor. That means the interrupt which has been occur has been serviced. Then what happens? Microprocessor will pop all the addresses from the stack, and it stores it in the instruction pointer. It stores it in the instruction pointer, and then starts executing instruction number 26. So look at that. This is the program P that we are executing. Suddenly we interrupt occur. So what happens? We are jumping to the interrupt service routine ISR. When ISR is completed, we execute the rate instruction, and to call the ISR we use the call instruction, and to return from the ISR we use the rate instruction. Then we comes back to the program. That means we start executing for 26th instruction where we stopped at 25th instruction. Whenever an interrupt is occurred, it will be acknowledged by the processor at the end of the current memory cycle. That means, first of all, the current instruction which is executing by the interrupt by the processor has to be entertained. has to be entertained. So we are observing that first of all the current instructions or current memory cycles has to be finished. Then we can able to proceed to the next one. The processor then services the interrupt by branching to a several service routine written to handle the particular interrupt. So every interrupt has a particular interrupt service routine. For example, trap interrupt is a non-maskable interrupt. It has a special interrupt service routine with a particular vector address. Upon receiving the device, the processor is then instructed to continue with what was doing previously by the use of the return of the interrupt instruction. Needless to say, return of the interrupt instructions is basically the rate instruction through which it will return from the ISR to the main program. The status of the program is being executed must be saved first, where it should be saved. So status of the current instruction results, let's say the microprocessor is executing 25th instruction currently. So result of this instruction is going to be stored in the stack. Similarly, all the registers value, accumulator, base register, counter, data register need to be stored in the stack, and the address of the next instruction that is stored in the program counter or IP instruction pointer that also need to be stored in the stack. So preserving those registers which are not saved will be the responsibility of the interrupt service routine. Once the program counter has been saved, the processor will branch to the address of the interrupt service routine. How it will branch? Very simple. Call the address of the interrupt service routine. So address of the interrupt service routine is basically denoted by 2000, suppose. So we know that the opcode code segment is started from 20,000 to 20,000 plus 2,000. That gives us the original address where to jump. So 22,000 is the address where we need to jump. The status of the program is being executed must be saved first, and the processor register will save the stack, and the or at the very least the program counter will be saved. So preserving those register will which are not saved will be responsibility of the interrupt service routine. Once the program counter has been saved, the processor will branch to the address of the service routine. So it's the same statement by mistake which has been written here. So look at that, we are executing the main program P, and suddenly an interrupt occur from the device X. If that interrupt occur, we will accept the interrupt, microprocessor accept the interrupt, and it will be denoted by the INTA signal. An interrupt is coming through the INTR signal or NMI signal, and then we get the vector interrupt vector address, and then with the help of the call instruction we are jumping to the ISR, and we save all the necessary data in the stack of the current program P. And then what we do, we basically load the PC with the starting address of the ISR, that is vector address. Whenever the program is end, then we once again come back to the main program. If there is no interrupt, then we will continue the main program. If the interrupt is not accepted, that means the INTA bar signal is 1, that means interrupt is not accepted, then we will continue the main program execution. Next, as we studied, the microprocessor can serve several devices. There are two ways to offer the service. One is interrupts, one is by interrupt initiated IO, and another is by polling. In case of the interrupt initiated IO, the advantage is that microprocessor can serve many devices. Not all at the same time, of course, but it can be able to serve many devices. And another advantage is that when interrupt is not occur, microprocessor can do its job. But in case of the polled IO system, what happens is that unless all the interrupts has been serviced, microprocessor cannot able to perform the programming. So each device can get the attention of the microprocessor. So each device can able to get the attention of the microprocessor based on the priority assigned to it. So polling method cannot assign priority because it checks all the device in a round robin fashion. That means first interrupt is occurred for suppose 1 nanosecond, then second interrupt is occurred for 1 nanosecond, then third interrupt occurred for another 1 nanosecond, and at the fourth time, once again the first interrupt occur, second interrupt occur, third interrupt occur. So rotationally all the interrupt is being serviced in time shared manner. Most importantly, an interrupt initiated IO method, the microprocessor can also ignore or mux a device request for service, because it may possible that there are multiple interrupts is requesting interrupt 1, say interrupt 2, they are requesting the microprocessor at the same time or MPU at the same time, but we have observed that INTR priority is greater than INTR 2, then INTR 2's request is being ignored. But in case of the pole diode, it is not possible. So most important reason that interrupt initiated IO method is preferable, that the polling method wastes much of the microprocessor time, because in case of the polling method, microprocessor has to wait for a prolonged period of time until and unless the interrupt is being completed. But in case of the polling method, what happens is that in case of the interrupt initiated method, what happens is that during the time when interrupt is not occur, microprocessor can do its own job. So what is the purpose of the interrupt? Before moving to the purpose of the interrupt, let me take your questions now. So if you have any question regarding this part, you please ask. So I would like to request all of you, so if you have any kind of questions, you please ask. So due to a technical glitch, there is a connectivity problem, but I hope that now the connection has been established. So if you have any kind of questions, you please ask. Due to connectivity problem, there are technical glitches, okay, because of some technical glitches we have disconnected for a while. So I would like to ask you some questions regarding these points that till now we have discussed. So if you have any kind of questions, please ask. If you have any questions, you are advised to ask. If you have any doubt, you are advised to ask. So I would like to request you to ask questions. Due to some technical glitches, I am disconnected for a while, but now I am connected. So I would like to request you to ask questions. So please ask questions. Aman Chaudhuri is writing, no sir, please proceed. I am waiting for the further questions. I am waiting for the further questions from your side. I am waiting for the further questions from your side. I am waiting for the further questions from your side. Please ask questions. Do not hesitate. Any further questions from your side? Aditi Ghosh is writing, no questions, sir. So let us proceed to the next next slides. So we are discussing basically, so interrupts are used to avoid trying down the microprocessor. To understand what is the purpose of interrupt, first of all, to understand the difference better, consider this example. Polling method is very much similar to salesperson. The salesperson go to door requesting to buy his product. Like processor keeps monitoring the flags or signals one by one for all devices. So processor is going door to door and requesting all the input device, output device, and asking whether they need any kind of services or not. But interrupting initiated IO or interrupt is very similar to shopkeeper. Whenever an input device requests the service, they come to the shopkeeper, that means microprocessor, and whoever needs the service or product goes to him, approaches him. Like when the flags or signals are received, they notify the processor that they need its service. So interrupts are using IO device with low data transfer rate, because you see input device and output device, they are mostly electromagnetical, electromechanical, electro-optical devices, but microprocessor is typically integrated circuits, so electronics devices. Naturally IC circuits devices are very fast than input and output device, so there is a very slow data transfer rate, like keyboard or mouse, in which case polling devices wasted valuable processing time. So in case of the interrupt initiated IO, we can save lots of time, processing time or CPU time or microprocessor time, because whenever the interrupt is not there, microprocessor can do its there is no job, no interrupt related issues, microprocessor can continue its operation. So we are observing that we have a keyboard interrupt here. Whenever this interrupt occur, microprocessor will call the interrupt service routine, which serves the keyboard, which basically solves the interrupt generated by keyboard. So keyboard is requesting for the input, then again control will come back to the main program. Again, suppose there is a printer interrupt. Printer has requested the microprocessor to generate the output. So microprocessor serviced it, and then once again it will come back to the main program. Again, suppose main program is continuing, and again printer has requested, again main program is continuing, keyboard has requested, after that main program continuing. So you see that in these stages, microprocessor can able to perform its normal operation, so less amount of time is wasted. Apart from this particular time, rest of the time is being utilized for the programming purpose. So which are the types of interrupts? In general, interrupts is of two types: software or internal, external or hardware. So interrupts are triggered by a software instruction that are typically known as the software interrupt, and operated similarly to the jump or branch instruction. Software interrupt example is suppose INT that in 8086 that can be there. So INT 00, double N stand for air, N value is 0, and this N value is also 0. So this is the divide error interrupt. Then 01, that is a single step interrupt. 03, that is a breakpoint interrupt. 04, that is the signed number overflow interrupt. Why divide error interrupt occurs? If I try to divide any number, say 23 divided by 0, then divide error, then actually the value is infinity or undefined. So then the divide error interrupt occurs. Single step interrupt is basically occurred when the trap signal is occurred. That means the microprocessor has to finish its job immediately and then go to some other points. Then breakpoint interrupt occurs when we are basically we need to break from one portion of the main program to another portion. We need to stop the program and we need to restart the program once again. Signed number overflow occurred when we are basically adding two numbers when there is the summation is too large to accommodate in a register, and when we are subtracting to signed number when the result is too small, result is a small negative number to be accommodated in a register. So hardware interrupts are generated by hardware devices when something unusual interrupt happens, and this can be by pressing a key, mouse or etc. In case of 8085, if we talk about the trap, RST 5.5, RST 6.5, RST 7.5, these are all considered to be the hardware interrupts. They are all generated from the hardware sources. Okay, and in case of the software interrupt, we have observed that. INT, that is the software interrupt. Maskable interrupt, we have already learned that the interrupt which are maskable in nature, that means can be ignored by the microprocessor, they are known as the maskable interrupt. Maskable interrupt. For example, in case of the 8085, if we talk about RST 5.5, RST 6.5, RST 7.5, they are all maskable in nature, and in order to set them maskable or unmaskable, we use the sim instruction, and in order to read the maskable condition, we use the rim instruction. But next is a non-maskable interrupt. We are observing that in case of the 8085, we have a particular print just like trap in 8086, the trap in 8085, we have an NMI interrupt. So there are some interrupts which cannot be masked or ignored, or which has to be accepted by the microprocessor. So these are basically non-maskable interrupt. So these are associated with high priority tasks which cannot be ignored. So in general, most of the processors support non-maskable interrupt. This interrupt has absolute priority. When it occurs, the processor will finish the current memory cycle and then branch to the special routine called interrupt service routine written to handle the interrupt request. For example, whenever trap occur, we will call the interrupt service routine or ISR, which will solve the trap. What is the starting address of the ISR 0024H. That's the starting address of the ISR for trap interrupt in 8085. That's an example of a non-maskable interrupt. Whenever any interrupting device will generate the trap request, microprocessor does not have any option. Microprocessor has to stop its current program execution and go to the subroutine. Interrupt service routine. For every interrupt, there must be an interrupt service routine or interrupt handler, as I told earlier. So when an interrupt is ignored, the microprocessor runs the interrupt service routine. For every interrupt, there is a fixed location in the memory that holds the address of the ISR. For example, in case of the trap interrupt in 8085, that fixed location is 0024. Okay, so the group of the memory locations set aside to hold the ISR is called the interrupt vector table. So where all the vector addresses are basically, or where the starting address of the interrupt service routine is stored, or the starting address of the interrupt service routine is stored in IVT, interrupt vector table. When an interrupt is occur, then microprocessor stops the execution of the current instruction. It transfers the content of the main counter into the stack, and it saves all its value into the stacks, and it all stores the current status of the interrupt internally but not on the stack. After that, it jumps to the memory location specified by the IVT. After that, the code written on the memory area will execute. The first 1 kilobyte of memory in 8086, that is 00000 to 003FF, this is the first 1 kilobyte area, is set aside as a table for storing the starting address of the interrupt service procedure or interrupt ISP. Since 4 bytes are required for storing the starting address of the ISP, the table can hold max to max 256 interrupt procedure. So that means max to max there are 256 number of interrupts. Starting address of an ISP, that is interrupt service procedure, is often called the interrupt vector. So as I told you earlier, the starting address of the ISP or interrupt service routine or interrupt service procedure is known as interrupt vector or interrupt pointer. Therefore, the table is referred to as interrupt vector table because it basically stores the starting address of all the interrupts. In this table, IP value is put in as low word of the vector and CS is put in the higher vector. Okay. IP stands for IP stands for the instruction pointer. So instruction pointer basically holds an offset value, as we all know. So offset value is considered to be the low words of the vector, and CS will put as a higher order in the vector. So we are observing that here is the interrupt vector table. So this is the vector 0, which is a divide error type of interrupt. Vector 1 is a single step. Vector 2 is a NMI non-maskable interrupt. Vector 2 is a breakpoint interrupt, and vector 4 is basically overflow interrupt. Vector 5 to vector 31 is basically reserved by the microprocessor for further operations. Vector 32 to vector 256 is 255 is available for the user, and we are observing the memory address of the each vectors. For example, vector 0, it is for divide error vector. 00 is basically stores the IP value of vector 0, and C02 is basically storing the code segment register value for vector 0 type of interrupt. In this way, we can able to store all this interrupt. For example, 04, this memory address is basically 04 means actually we are basically meaning 0000004. Actually, we are trying to mean that. So 04 is basically storing IP1, that is instruction pointer 1, which is the instruction pointer for the vector vector 1 or the single step interrupt, and 086 is basically storing the code segment register value for the single step interrupt. In this way, NMI, breakpoint, overflow, reserved and user available interrupt all are calculated. So it has started from 00 and it has ended as a 3FE. So to the memory range of the interrupt vector table is 00000, and it will continue up to 003FE. So which we have observed that it is continuing up to not E, to 003FF. So it is 3FF. Now let's talk about the 8086 interrupt. So we are aware of the fact that the interrupt can be either hardware or software. So if the interrupt is generated by the inbuilt device like timer or the interface device such as memory interface, IO interface, they are called hardware interrupts. Okay, and if the interrupt is generated by the software code, suppose we are running a program and suddenly while executing the output or displaying the output there is an infinite loop is rotating, or suddenly the program has stopped. For example, in the few minutes back, due to some technical glitches, my YouTube live streaming and my internet has crashed. So this can be treated as a software interrupt. So in other words, 8086 interrupt can come from one of the three resources. Which are the resources? First is an external signal applied to a non-maskable interrupt input pin or the input interrupt pin, that is a hardware interrupt. It can be generated by a software resource, then it is known as software resource. Some error condition produced by 8086 by execution of an instruction. For example, we are dividing, suppose we are performing this operation, intex AL comma BL, where the value of the AL is basically 0 and the value of the BL is basically supposed 255. Then obviously value of the BL is supposed FF. Then naturally there is an interrupt occur because this is a divide error interrupt or divide by 0 interrupt. Interrupt is the same as exception in Java. Interrupt is same. So if you attempt to divide and operand by 0, the 8086 will automatically interrupt the current executing program at the end of each instruction cycle. The 8086 checks to see if any interrupt have been requested or not. If an interrupt has been requested, then 8086 responds to the interrupt by stepping through the following series of major actions. First of all, it decrements the stack pointer by 2 and pushes the flag register, that means the sign flag, carry flag, step flag, direction flag, over flag into the flag register first. Second step, what it basically does is it disables the 8086 INTR interrupt and input by clearing the interrupt flag in the flag register. Sorry. Next step is that it resets the trap flag in the flag register. Fourth is it decrements the stack pointer by 2 and pushes the current code segment registered in the content of the stack. So first of all, the value of the stack flag register is pushed into the stack. So suppose the value of the flag register is 1 2 3 4. Now it is pushed into the stack. Okay, then what happens is disable 8086 INTR interrupt. So whatever, suppose this is MPU of 8086, so whatever the INTR in the request is coming through this ping, it will simply disable it by disabling the interrupt enable flag. So if the interrupt enable flag is 0, naturally INTR request will be negated. Okay, so now this pushes the content of the code segment register in the contents of the stack. Suppose the value of the code segment is 2000, so it will push it into the 22 into the stack. So 20 first, then 00 will be pushed into the stack. Now stack pointer is pointing this position at the top of the element, which is 00. Then what? It decrements the stack pointer once again by 2 and pushes the current instruction pointer contents to the stack. Suppose the current instruction is basically pointing the displacement value 0400. So 04 will be placed, then 00 will be placed in the stack. Now the stack pointer is pointing 00 location. After that, 8086 will automatically do a type 0 interrupt. So what is basically the divide by 0 interrupt? It is automatically do a type 0 interrupt if this is important, if the result of a div operation, div stands for division operation, or an IDIV operation. IDIV stands for interrupt instruction divide operations, is too large to fit the destination register. For a type 0 interrupt, 8086 pushes the flag on the stack, resets the trap flag. Resets trap flag means trap flag becomes 0, and TF flag means trap flag also 0, and interrupt enable flag also becomes 0, and it pushes the return address of the return address of the stack. Return address means, suppose this is your ISR has started from 80,000 and it has ended to 80,005. So 80,005 is your return is your last address, and now your main program is basically starting from say 70,000. So 70,000 is basically the return address where your control must need to be come back for after executing the rate instruction present in 80,005. Our next interrupt type is single step interrupt. The use of single step execution feature is found in some of the monitor and debugger programs. When we tell a system a single step, it will execute one instruction and stop. And when we can then examine the contents of the register and memory locations. In other words, when a single step mode of a system will stop after it executes each instruction and wait for the further directions of the user. The 8086 trap flag and interrupt 1 type 1 interrupt response make it quite easy to implement a single step feature direction. So what is the use of the single step execution? Single step execution feature is found in some of the monitor debugger program. When we tell a system to single step, this is important point. So when we tell a single step, it will execute one instruction. It will execute one instruction and then it will automatically stops. It will not be able to go to the next instruction that to be executed, etc., etc. It will not able to increment automatically the value of the instruction pointer. Next is non-maskable interrupt, which is type 2 interrupt. The 8086 will automatically do a type 2 interrupt, which is a non-maskable interrupt response when it receives a low to high transition in the NMI pin. So previously, before the non-maskable interrupt, NMI pin is low or 0. When non-maskable interrupt signal is coming to NMI pin, it becomes 1. As simple as that. When it does a type 2 interrupt, 8086 pushes the flags on the stack, reset the trap flag, that means the trap flag becomes 0, reset the interrupt enable flag, interrupt enable flag becomes 0, and then it pushes the value of the code segment, because the code segment basically holds the opcode of the current instruction, and the value of the IP. Why IP? Because IP is instruction pointer, it points the next instruction that to be executed. So the value of the IP is also pushed into the stack. It will then get the CS value from the start of the type 2 interrupt service procedure and from the address 0000AH, and the IP value of the start address of the procedure address is 000008H. There are several other types of interrupts such as breakpoint interrupt, that is type 3 interrupt. This type 3 interrupt is provided by the execution of the INT3 instruction. INT3 stands for interrupt 3 instruction. So it is a breakpoint interrupt. What is the main use of the breakpoint interrupt? To implement breakpoint. To implement breakpoint function in the system. Whenever we insert a breakpoint, then what happens? The system executes the instruction up to breakpoint, and then it goes to the breakpoint procedure. We have already learned, we are about to learn the database management system. If we are already learn it, we know that what is breakpoint and what is rollback. If we use the breakpoint, then we will continue up to breakpoint, and again then we come back to the initial position. Next is overflow interrupt, which is a type flow interrupt. For example, we have an 8-bit signed number, which is this one, and we have an 8-bit signed number, which is this one, and result is this one, and we would be correct the result if we are adding the unsigned binary numbers, but it is not correct signed result. So this result is not a correct signed result. So in that cases, overflow flag occurs. So we are observing that how many bits are there? 1, 2, 3, 4. There are total 8 bits present in the first data. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Total 8 bits are present here. 1, 2, 3, 4, 1, 2, 3, 4. But it is representing, but it is not coming in the 2's complement form. It is, it will be correct if we are adding unsigned binary numbers. So as because it is presented in the not in the 2's complement form, hence there is a problem occur. So 8086 overflow flag will be set. When it is set, if the signed result of the arithmetic operation on two signed numbers is too large to be represented in the destination register or a memory location. Next is software interrupt. Software interrupt has started from 0 to 255, and next is so what is software interrupt? The 8086 INT instruction can be used to trigger the 8086 to do any one of the 256 possible interrupt types. We have observed in the interrupt vector table these types of interrupt from 0 to 255. The desired interrupt type is specified as a part of the instruction. That is important. The instruction INT32, that means interrupt number 32, for example, will cause 8086 to do a type 32 interrupt response. So it basically helps the 8086 to take the response from interrupt type 32, and 8086 will push to the value of the when it received the interrupt request signal from INT32. INT32, then what it does, 8086 puts the flag register value on the stack, reset the trap flag and interrupt enable flag, and push the value of the CS and IP values to the next instruction. Next is INTR interrupt. INT stands for interrupt or for request, and there are total 0 to 355 number of types of it. The 8086 INTR input allows some external signal to interrupt execution of the program. Unlike NMI input, however, INTR could be masked so that it cannot cause an interrupt. If interrupt flag is clear, then INTR input is disabled. And if IF is clear, then at any time with clear instruction. So we are observing here in this table several types of interrupt related instruction. For example, CLI will perform the act. So if we clear interrupt flag becomes 0, and the flag affected is IF. Next is STI. STI stands for set interrupt flag. ST is for set interrupt, and it says set and I for interrupt. So set interrupt flag, whenever this flag is 1, then a flag is affected. INTN, here it is basically the software interrupt. The value of the n can be anything from 0 to 255. So what happens is that first of all the stack pointer will be decremented by 2, our flag register inserted over there, trap flag and the interrupt flag is become 0, then code segment is inserted into the SP-4 and SP-4. Then what happens is that IP will be set with the SP-6 and 4 into n, that gives you the correct value of the IP. Then is irate. Irate stands for I for interrupt, rate for return. So irate interrupt, what happens? First of all, we push the value of the IP to the stack pointer, then we push the value of the code segment to the stack pointer +1 +2. That means we plus 2. For example, suppose this is basically my stack. This is my stack is pointing F. Then if I decrease, first of all we will place some value into the stack. So the value, suppose into the stack that we are about to push is 1 2 3 4. So now this is the top of the stack. Now the stack pointer is basically incremented by 2. So now this placement placed, these two places are also going to be used. Now stack is increased where the code segment is basically stored. Now again stack is incremented by 2 and now the data segment is going to be stored over there. The flags is going to be register value will be going to be stored there. Then again stack is incremented by 2. Then the value of the stack pointer is basically stored over there. Next is into. INT stands for interrupt, O for overflow. Whenever there is a overflow occur, this flag is set or reset. Which flags are basically used here? Trap flag and interrupt enable flag is used there. Halt. What is the purpose of halt instruction? I have already explained in several programs of 8085. So whenever halt instruction occur, current program stops and we will go back to an initial address. For example, whenever we are executing RST0 in 8085, whenever halt instruction occurs, we stop our program and we'll jump to the address 0000. Next is wait. Wait for the test bar input to go active. None of the flags is affected in this case. So we have observed the different types of interrupts and different types of their example. Now about the interrupt priority. So 2 or more interrupt may occur at the same time, but one interrupt has to be serviced first. So how to decide that if both of them comes at the same time? So that is why we are using the interrupt priority. For example, the address of the interrupt 0 and 2, both of them suppose comes at the same time, but external interrupt 0 has the higher priority than external interrupt 2. So 0 to be executed first, then 2 to be executed. Next is interrupt pins and timings. First interrupt pins is INTR. INTR stands for INT for interrupt, R for request. So it is activated by the peripheral device to interrupt the processor. That means for input and output purpose we are using this interrupt. It is label trigger. That means label can be 1 or 0. 1 means it is active, interrupt is activated. 0 means interrupt is deactivated. Next is INTA. INT stands for interrupt, A for acknowledgement. It is activated by the processor to inform the interrupting devices that the interrupt request is accepted. Next is NMI. NMI stands for non-maskable interrupt. Whenever the major system falls, say power failure, motherboard crash, hard disk crash, these types of interrupts will occur. So first of all, it is edge trigger. That means it will occur in the positive edge or the negative edge. 0 stands for the negative edge and 1 stands for the positive edge. Okay, so say if there is a 0 to 1 transition, it is considered to be the positive edge. If there is a 1 to 0 transition, it is considered to be the negative edge. So must remain at logic 1 until it is accepted by the microprocessor. Before the 0s and 1s transition, NMI must be at logic 0 and at least 2 clock cycle. So no need for interrupt acknowledgement, because whenever the interrupt is coming from NMI, then we automatically know the interrupt is accepted. So no need for the microprocessor to inform the interrupting device, yes, your interrupt has been accepted, because if the interrupt is coming through the NMI signal, it should be accepted. So this is basically the timing diagram and the peak diagram here. Look at that. Whenever there is a transition from 0 to 1, INTR value is basically activated. INTA bar is informing the device when whether the interrupt is accepted or not. You look at that, there is a transition from 0 to 1, and we are observing that to travel the data of code whatever, we are using the data bus D0 to D7. So thank you all for joining this lecture. Now I would like to take your questions. Can you please explain again the interrupt priority? Very simple. If there are two interrupts, say interrupt X, interrupt Y. Two interrupt is basically requesting the same microprocessor at the same time. Then microprocessor what will do? Interrupt X will be executed fast or interrupt Y will be executed fast. That will be decided by the interrupt priority. Interrupt priority is given below. Just like we have a several several operators in C, plus, minus, multiplication, division. So we need to understand that division has the higher priority, then multiplication, then addition, then subtraction. So we need to follow this procedure. Bracket has the higher priority, exponential has the higher priority. So in this way. So if you have any kind of question, I will be available for the next 4 minutes. If you have any kind of question, please do not hesitate and please ask me whatever your questions are related to the interrupt. So related to the interrupt, whatever your questions, you please ask. Whatever your doubt, you please ask. Your examination link and attendance link is given. You have to give the examination or attendance for this class. So if there is any kind of question, please ask, or else I can stop my lecture. Aishwarya Roy is writing, thank you, sir. So I'm waiting for another 2 to 3 minutes for your responses. Syllabus of the first midterm will be announced at 15th September. Syllabus of the first midterm examination for MPMC theory will be announced in the 15th September. If you have any kind of doubt, please write it down. Aishwarya Rai writing, no questions, sir. I am waiting for other students for their reply and for their responses. Aman Chaudhary writing, no questions, sir. Thank you. Let us take other questions also. Let us wait for another 2 minutes and wait for the questions. I believe that there are some questions. I will definitely circulate the PDF document of the today's lecture, that is Intel 8086 architecture, Intel 8086 interrupt, Intel 8086 assembly level languages via your official Telegram group. So no problem about that. If you have any kind of doubts regarding divide by zero interrupt, single step interrupt, point breakpoint interrupt, overflow interrupt, please ask. I'm going to wait for another 1 minute for the students for their replies and their responses. Preyoshi Paul is writing, no questions, sir. I'm waiting for the other students for their replies. I'm waiting for other students for their replies. So thank you all for joining this lecture. One question come, whenever a number of devices interrupt, whenever a number of devices interrupt a CPU at the same time, how the processor handles them. Whenever different interrupts is being requested to the microprocessors try to find it out what is the priority of the interrupt. Suppose INT1 and INT2 both interrupt occurred at the same time. We need to find it out what is the priority of the interrupt. Priority of the interrupt is stored in the priority table, which is kept with microprocessor. So microprocessor goes to the priority table or interrupt vector table, priority table, and find it out which interrupt has the highest priority. Then according to that interrupt will be serviced first, and the request of the other interrupt will be ignored. For example, if INT1's priority is greater than INT2, then INT1 will be executed first, then INT2 will be and INT2's request will be rejected. So I hope there is no other questions. So we are ending our lecture here. Thank you all for joining this lecture. We shall meet tomorrow once again.